Somebody is like eating their mic.
It's not me.
Aaron, your beard on the mic. Is your beard on the mic?
This episode is sponsored by Front-End Masters. Engineers have watched over 2 million hours of Front-End Masters videos to upgrade their skills in the latest best practices in front-end development and Node.js. Popular video courses of theirs include courses on advanced JavaScript, Angular 2, React, API design with Node, and functional and asynchronous JavaScript. Many of their teachers have even been guests on JavaScript Jabber. Check them out at frontendmasters.com.
Hey everybody, and welcome to episode 241 of the JavaScript Jabber Show. This week on our panel we have Joe Eames.
Hey everybody.
We have Aaron Frost pinch hitting for us.
Hello.
I'm Charles Max Wood from devchat.tv. Just a quick shout out about DevOps Remote Conf and JS Remote Conf coming up in January and March. You can still get tickets. I think you can still get early bird tickets, but not for very long. We also have a special guest this week, and that is Lee Byron.
Hi everyone, good to be here.
Now, Lee, we've had you on. Were you on Ruby Rogues? Is that where you were on before?
I think so, yeah. A while ago, talking about GraphQL.
Yeah. So somebody said Immutable.js, and you're the guy. So do you want to introduce yourself, and then we'll talk about what Immutable is and why it is and why it's cool?
Sure. So I work at Facebook on a team called Product Infrastructure, where we build tools, languages, libraries, those sorts of things in service for product teams to help them build better products. So in the course of my time there, I've worked on a lot of stuff, including React, GraphQL, and Immutable.js. Very
cool. So what is Immutable.js? What does it do, and what's the payoff that people are looking for there?
Yeah, so it's a JavaScript library that implements a collection of data structures that are really interesting. They're called persistent immutable data structures. And what they do is they let you sort of describe a collection of data. So there's two major kinds of collections that we've built in there. One is a list, which is, going from one side, kind of like an array, one side to the end with a bunch of values in it. And then we have a map, which is a keyed collection. So at this key, what is the value? So for those two kind of abstract collections, we have persistent immutable implementations of them. And what that means is you can create one of these collections, and then rather than editing it like you would, set an index into an array or set at a key in a JavaScript object, you actually create a new copy of that thing with the change applied. So the previous version doesn't change, and then the new version has that change applied. And lots of really interesting things happen once you have this property of immutability in all of the previous versions. That's what it means by being persistently immutable, is that all of the old versions persist after you have the new version with the change applied. There are versions of immutable data structures where the old ones, as soon as you don't use them anymore, they start to kind of degrade as pieces of them get recycled. So that's not what we have here. But what happens is when you have these things, if you have the same reference to one of these collections, you know for a fact that nothing has changed about it. But if you have, say, you have a JavaScript array, and you call push on that, you push another object onto that array, and then you say, like, okay, I have this array, triple equals, here's the previous array I had, and it comes back true. Well, you have no idea if that array had changed under the hood. In fact, yeah, we'd called push on it, so it had changed. And not being able to know just with triple equals if something has changed or not, you throw away all these really awesome performance techniques that you can use in your apps. The primary one being memoization, where every time you want to compute something, you look at your previous input, and if the new input you got is the same, you just don't do the computation. Instead, you take the output of that computation last time and you reuse that. And it turns out that trick is extremely helpful for building UI applications, especially when you have a component library like React.
So first question, I've got a big list of data, and instead of just say it's a big list of users, and instead of modifying one of the users' first names, I have to create a whole new structure. Obviously, that's 100 times slower, right?
Great question. So this is, of course, if we were to build this in the most naive way. So let's back up and say, All we really want to do is have a JavaScript array, and then I just want to treat it like it's immutable. So in order to do that, we would have to do exactly what you just said. We want to change something in one of the objects in that array, and in order to make that change and not mutate the array, we'd first have to copy that whole thing, and then in the copy we could make our change. And that would be really slow because every time we're changing anything, we're just copying everything. Well, the cool thing about persistent immutable data structures is that while they give the appearance of being like an array, like a list, actually under the hood, they're trees. And so when you have a tree, you can do this really cool thing where you recycle parts of the tree that definitely haven't changed in an operation. So if you ever had to study stuff like a B tree or binary trees, you can imagine in your head kind of walking down from the top down to one of the leaf values, and then imagine all that stuff that you never touched walking all the way down to that leaf value. All that stuff gets recycled, and only the stuff that you touched along the path to get to the value you're actually changing ends up needing to get copied. And in practice, that ends up being a very, very small percent because we have very wide trees rather than very deep trees for these data structures.
So it's essentially a tree of diffs?
It's a tree of values. So when you do these diffs, or when you're creating a new version of the immutable data structure, you're actually taking the old tree, and then you're creating a new tree that's going to have the new value in it. And then as you're doing that, any parts of the old tree that you know for sure aren't going to change, you can just recycle them wholesale. No copying, you literally just point to the same spot in memory. And then for the parts that do change, you're creating new branches in the tree for that part that did change. And so what that gets you is when we talk about performance, we often talk about like O of 1, O of n squared, stuff like that. So if you're in the naive approach where you just copy everything first, then you make your change, that means that changes are O of n, right? You have to take the size of the whole collection in mind anytime you make a change. When you're mutating data directly, we say it's O of 1. Right? You only have to consider the one piece of data that you're changing. You don't have to consider anything else about the collection. With persistent immutable data structures, it's O of log n. So you take the log of the size of the collection, and that's roughly the amount of work that you end up doing to make one of these changes.
For people that aren't necessarily familiar with Big O, could we get like a very brief explanation and specifically how log n fits into that, like in some, like some maybe real terms?
Sure. So when we say n just stands for some like maximum number of the thing that we're talking about. So say we have an array of 100 items in it, and we want to make an immutable copy of that array. So first we're going to call like array.slice or something to get a copy of that array. And that's going to have to, go through that array and every one of the 100 slots in it, look at that data, and then copy it over to the new array. So it's going to take 100 operations to do that. So we say that it's O of n, which stands for order of n being the largest number, n operations. Then if we were just going to mutate that array, we care about one thing. We could have an array of 10 things, 1,000,000 things. It wouldn't matter. We're only updating one piece. So there we say it's O of 1 rather than O of n, as we didn't even care about the size of the array. We only cared about the one thing that we changed. So then you can start to play with that n. You can do n squared means, if you have an array of size 100, well, it's going to take 100 times 100 operations to do the work that you want to do. When we say O of log n, that means the logarithm of n, so the opposite of taking a power. And so for 100, that might be something like 2 or 3. And when we talk about the big O notation, we often drop the coefficients of these things. So when you say something is like 2n or 3n, we just say n. But in practice, that stuff, it matters, especially when you're talking about relatively small amounts of data. When I say relatively small, I mean like, a couple thousand things in a list. The difference between 1,000 operations and 2,000 or 3,000 operations, that's sizable. That's a 2 or 3x difference. So when you take that kind of computer sciencey terminology of the big O notation, you convert it into the real world performance tuning, you have to be really careful about that. So where that plays into this is we say, okay, it's log of n. But if you remember logarithms have a base. Is it logarithm base 2 or is it logarithm base 100? right? Those are going to have very different numbers that come out. With persistent immutable data structures, it's logarithm base 32, which is a pretty big base for a logarithm, which means you can have something like 1,000 items in a list, and with 1,000 items in the list, that log base 32 is going to get you something like 2 or 3 or 4, as opposed to a log of base 2, which might get you 10 or 20. And so we're talking about like, much, much faster. So oftentimes when we're talking about these data structures, we say, oh yeah, updating these things is about as fast as just mutating a regular array. We say it's really close to O of 1. But in practice, it's O of log n. Hopefully, I'm starting to paint a picture of what these things look like. The fact that when you're making a change, you're not making a copy of everything, but you're also doing something that's pretty fast. So what these things do that's really cool is it gets you this nice balance where you get the properties of immutability, where as if you had just copied everything, and that gets you really awesome programming capabilities. But if you do that naively, it's really slow. So by using these really interesting data structures, you can get the same techniques, except that you can still have the same level of performance that we're used to in our mutative imperative programming languages like JavaScript.
Right. So a couple of questions came up as you were describing that. First off, when you were talking about this internal structures of trees, so as you make a new copy, when you don't have to actually copy most of the elements, you only have to change 1 or 2. Does that mean the new tree, it encodes all of the information as to where each of the end nodes are, and that's all it contains? Okay.
Yeah, that's right.
Okay. So another question that came up is, since it's a tree, but you said it acts like an array, right? We're talking about the immutable version of JavaScript's array.
Yes.
It's implemented as a tree. Obviously, arrays and trees have different performance characteristics. Does that ever matter?
Yeah. I mean, that's kind of what I was talking about before, where, changing something in a list, changing something in an array, they're going to be slightly different performance characteristics. And in fact, Immutable.js data structures, in terms of just raw speed on inserts, will just never beat mutating an array. It just can't be done, right? Mutating an array is the fastest possible way of inserting something into an array-like data structure. Immutable.js gives you something that's array-like in the sense that it has a length, it has index 0, it has index length -1, it has all the indexes in between. So it's array-like in that sense, but the way that that data structure is actually built under the hood is very different from just a block of memory.
Right.
And in fact, most programming languages that you use, unless they tell you very explicitly that that's what they're doing, when you say, give me this array, under the hood, they themselves are probably not just allocating a block of memory, where when you say, all right, now give me index 3, and it's giving you the third byte in that block of memory, that's not what they're doing probably. They're probably doing something a little bit more sophisticated. JavaScript engines in particular do all kinds of weird things. I have an array of size 1 billion, and it's like, all right, great, that was very fast, because it doesn't actually create 1 billion items. It just says, here's an object, and then we'll have a length property with 1 billion. And you're like, all right, now insert index 1 million, and it's not going to create 0 through 999,999 for you. It's just going to create in just that one piece. And so it's really different from what an array actually is. If you have like a C array or an array in any language that truly gives you an array of memory. But, the trick to all this is when we talk about arrays, we don't care about the memory underneath unless we're truly bit-fiddling C programmers. When we're in JavaScript or any of these high-level languages, we really just care that it has a length, it has index 0, it has index length -1, it has all the indices in between. And then how it's actually implemented under the hood lets us trade different kinds of performance profiles with characteristics that we want. So with the JavaScript array, it lets us have really, really, really big arrays for free, and that's a nice performance characteristics for JavaScript. With Immutable.js collections, it gives you immutable data structures. So every time you make an edit, you get a new version of that data structure with the change applied. The old ones don't change. And so you pay a little bit of performance cost for that. So the hope is, when we're talking about performance, we want to back away from micro performance benchmarks. So it's really easy to say, okay, here's what I'm going to do. I'm going to create an array, and then I'm going to write a for loop, 0 to 1,000. I'm going to go, all right, index at 0 is equal to 0. Index at 1 is equal to 1. Index at 999 is equal to 999. And now I'm going to time that. And I'm going to do the same thing for Immutable.js. I'm going to create a list. And then I'm going to do a for loop, 1 to 1,000. Set at 0 is equal to 0. Set at 1 is equal to 1. And do the same thing. Yeah, a list is going to be slower. Like a Immutable.js list is going to be slower than an array. And so it would be short-sighted to say, oh, well, that's slower. I don't understand this. I'm going to toss it off. Why would I use this to make my app slower? What we really want to do
So let me interject.
Please.
I'm going to be short-sighted. Why in heaven's name would I want to do this then?
Because when we're building apps, we are building big, complicated things that have all kinds of really interesting interdependencies, where the performance characteristics of the whole don't look like the performance characteristics of the micro at all. So making an array insert twice as fast or twice as slow is probably not going to have a meaningful effect on almost any JavaScript application out there. But what we do care about is taking the computations in our apps that are the most heavyweight and trying to reduce those as much as possible. So when we're talking about UI applications, that's primarily figuring out like what changed in my application, what views need to get re-rendered, re-rendering those views and figuring out that sub-views also need to re-render. Like these are the things that are actually slow about our apps, not inserting and removing from arrays. So It turns out that there's all kinds of different techniques that we can apply to make those kinds of problems less expensive. But one of my favorites is memoization, which I talked about before, which is like, if the world hasn't changed, don't do anything. It's basically the idea. So if you say like, all right, what changed? Something changed. I saw some update. Oh, but my particular piece of the world has been left unchanged, so I'm not going to bother redrawing onto the screen. It turns out that if anything in your data could change at any time, and figuring out what has changed is itself very expensive, then you end up balancing these things like, well, should I do the work of like digging in and trying to figure out whether or not something changed or not? Or should I just like damn the torpedoes and re-render anyway? And if you're like stuck balancing, I don't know which one's going to be faster, I'll just do the simpler thing. Well, what if I told you that figuring out if something changed is just using triple equals? You're like, oh, well, that's easy. If the old one triple equals the new one, return, do nothing, bail. Otherwise, all right, keep going and re-render my views. And so you can't do that with JavaScript arrays and JavaScript objects. You can't use triple equals to figure out if they're the same or not, because of course someone could have inserted something into there, or you could have done that in another part of your program. And so it's really hard for the program to figure out in a performant way that something has changed or something has not changed. And so that is the crux of why immutable data is really interesting for building these sorts of applications, like UI applications, where the high-level stuff is expensive. And what we hope is that in aggregate, not only do the two things balance out, that, okay, yeah, immutable data structures are slightly slower than pure arrays and objects, but in exchange for that, I get to skip a lot of this work that's really expensive. What I found in actually using this stuff to build real things is not only does it balance out, but it swings widely in the favor of much faster apps.
So I've seen a few. Sorry, go ahead, Aaron.
No, I just was going to say, going back to your very first example of this micro performance measuring that people are doing, the creation of the 1,000 length array versus the 1,000 length immutable array, the performance on creating the structure is slower with Immutable.js. But then when you need to check to see if anything's changed, immutable is just a simple triple equals, whereas the array you have to now traverse. It's an n operation. You have to go through each one, right?
That's exactly right.
And you do that way more than the initting of the data structure itself. So that's a massive performance gain.
That's the thought, and it's not obvious at first glance, because if you're used to building JavaScript apps, then comparing two things isn't a thing you do all the time. You're not doing that more, because you know, like, okay, if I have to walk through both of these two arrays and then compare each item in the array, that's going to be really expensive, so why would I even bother? But what's really interesting is when we change the performance characteristics of some of these techniques, all of a sudden they're like, oh, well, that's really cheap, so I'm just going to do that everywhere. As soon as something becomes easy and very fast, then programmers will immediately recognize it as a technique that we should just be like sprinkling over everything. And so once you start building apps this way, then you realize like, oh, wow, like, yeah, that part of my app got a little bit slower. I traded in O of 1 for O of log n. But this part of my app went from, I didn't even know what technique to use, so I was just like repeating work all over the place, to an O of 1 check, a very, very cheap check, to figure out if I should do anything or not in the first place before I actually go do the work.
Yeah, my brain went to the place of, well, I could just put a changed property on my array or my map. And then I realized, oh yeah, the last time I tried to build a change detection system, that was no fun. And so if you get it automatically, then it's, oh, okay, this is much simpler. Yes, I have to remember to do a mutable map or a mutable whatever, but then I do get the side effect for free.
Exactly. Yeah, I've had to build one of those change tracking systems as well with a little, the dirty bit flag, and it is not fun.
You forget it in one place.
Yeah.
Something breaks. That's
something breaks. Yep. Yeah. Or you end up with like some kind of race condition where one thing is like rendering something. It's like, okay, we rendered. Let's flip the dirty bit back to not dirty. And then meanwhile, like another part of your app is like updating that thing and it's setting the dirty bit back again. Like that happened to me. Yeah. That bug occurred a couple times, and then you ended up in this like, all of a sudden the browser starts like, hard looping and your fans on your machine start spinning. You're like, what is going on? And it's like this race condition between the two where there's bouncing back and forth between each other. So that's crazy. It's no way to spend your time as a programmer trying to debug those kinds of things.
Right.
Let's pause for a moment to talk about our sponsor, Taurus. Taurus is a new tool for managing and securing the secret information that allows your app to run. You know the stuff: passwords, API keys, database credentials, all the stuff that gives access to the private stuff that you don't want anybody to touch except for your application in specific ways. Taurus provides a convenient way to store all this information in the cloud, and they can't access it because it's encrypted with material derived from your password, which is never transmitted to their server. So it's secured from them, from everybody else, but accessible to you. This means only the servers, development machines, and applications you've allowed can access the information. So make secrets management headaches a thing of the past and check out Taurus today. You can find them at devchat.tv/Taurus. That's devchat.tv/TORUS.
So I've seen a couple of performance charts where people in different frameworks, I think I've seen this for both React and for Angular 2, where they said that using a mutable, the operation for change detection essentially goes down to O of 1. Is that pretty much true?
Yeah, exactly right. That is
which is pretty amazing, right?
Trade. Yep, that is the trade that immutable data makes for you, is operating on that collection. And let's compare it to where we were before. The benefits of immutable data is not a new phenomenon. It's as old as computer science is. The new thing, or relatively new, because a lot of these data structures were kind of discovered and perfected over the last 10 to 15 years. But before that, what we were saying is, well, change detection is so important that we're willing to make updates O of n. And that was like academia computer science for like decades. And it's no surprise that stuff never kind of like made it out of the academic labs into building real stuff, because the performance trade-offs just weren't balanced. They weren't right in aggregate for the kind of things that we're building and for consumer applications. Mm-hmm. But as soon as the academic research caught up, where we got these really interesting data structures that say, well, okay, we're going to give you the benefit that we've noticed is extremely beneficial in academia, but we're going to keep as much of that initial performance characteristics of inserts and updates and deletes as we possibly can. Then I think was the game changer. That's when you saw these things jump out of academia and start making their way into like consumer applications and production services.
So this kind of leads to another question I had, and that is that most of the people I talk to, when they talk about immutability, they're talking about functional programming. They're saying, well, we have all these characteristics that make functional programming the stuff, and it's so awesome. And immutability is one of those things. But yet it seems like Immutable.js, you're talking about benefits that benefit people in object-oriented or procedural land as well. So is there a connection there, or do people just shoehorn it into that box so they can ignore it?
The connection there is a connection from its history. So, you can really, I look at computer science as having this fork in the road that goes all the way back to even before it was like an academic field, where you have the difference between, Turing and his machine of, instruction by instruction, move left, move right, read, pull, shift, put, and illustrating that via his set of instructions, you could build anything. And that was amazing. And you have that become kind of the basis of the actual like electrical engineering and hardware industry behind computer science. It's no surprise that the basic set of assembly CPU instructions that goes all the way back from the first CPUs up till the same ones that we have in our machines today, they're sets of instructions that they read in a linear order, right? First do this, then do that, then do this, then do that. That goes all the way back to Turing. But we have this other fork in the road all the way back in I'm not sure what the decade is, I'm going to get my history wrong, but it was like in the early 20th century where, I'm trying to remember his name, I think it was Alphonso Church. I might be getting my early computer scientists screwed up. But the other fork in the road was lambda calculus. And so lambda calculus, it didn't come from a background of figuring out how to play these things in order and this desire to build a machine. That's what the first branch of computer science was trying to get us to, was like, let's build real stuff. But lambda calculus was from the world of logic and saying, well, logic and what we have there can help us compute anything. We can literally build anything from this. And from that early fork, lambda calculus, if you go look back at those original papers of lambda calculus from I think they're like the 1930s or 40s, it's Lisp. It looks like Lisp. And Lisp is one of the oldest programming languages, and it was based on lambda calculus. It was tried to be as a direct implementation of lambda calculus as possible. And from Lisp grew out all these other really fascinating functional programming languages and families of languages like ML and Haskell. And those all find their basis in lambda calculus. Whereas over in Turing land and our CPU instructions, people are trying to figure out, well, man, punching cards on a punch card machine sucks. So what else can we do? And it's like you get the first real computer languages, and pretty quickly into the history of computing languages, you get C. And then C, can compile down to that set of machine instructions. And from C, you get all the family of programming languages that most practicing software engineers use today. Everything from Java to JavaScript, Python, whatever. But what's happening now that I think is truly fascinating, it's been happening over the last 5, 10, 15, maybe years, is that these two worlds are coming back together in not just in academia, because of course academics are always looking at all of these different pieces of computer science, but in our jobs and in building consumer applications. We're seeing how pieces of the Alphonso Church branch, lambda calculus, functional programming world of computer science can be pulled into the Turing land, C, JavaScript, imperative, mutative programming model land, and how benefits from one can impact the other. And they go both ways, because for a very long time, there was just really no good way to build like a user interface with functional programming languages. That was true up until the last couple of years, really. I've tried some of them. They're all kind of a pain in the butt to use. And I think the first one that was truly exciting and fun to use was by this guy named David Nolan, who built Ohm, which is a wrapper around React that it runs in Clojure. And Clojure is a Lisp. It follows this long history line in terms of programming languages back to lambda calculus and functional programming, and it has immutable data structures, and it has everything that you would expect to find in that functional programming language. But he pulled from the consumer application user interface engineering world and showed that these two things actually could line up very well. So that, I think, built a bridge between these two communities, the functional programmers who want to build production stuff and production people who want to use functional techniques, who are now kind of like, we're in this really interesting time where there's lots of idea swapping. But to go back to the thing that you originally mentioned as I was started down this diatribe of, people say, like, oh, immutable data structures, they're only in functional programming languages. Well, that's where they started from, because in lambda calculus world, there's just no real concept of mutating a buffer of memory, because there was no concept of a buffer of memory in the first place to mutate. Instead, what you had was math. You had sets, right? You're like, okay, I have the set 1, 2, 3. 1, 2, 3 plus the set 4, 5, 6 equals the set 1, 2, 3, 4, 5, 6. Like, I didn't change the previous list sets. I just got a new set. That's just how math works. And so it made sense that lambda calculus, which came out of the world of logic and math, would take on those properties as long as they could. And so the people who are building these functional programming languages, their impetus was don't break math, right? Like, don't break math. Figure out how you can make the data structures and the computer science under the hood work such that this thing retains the properties of lambda calculus, math, and logic. Whereas in Turing land, the very first thing that we got was, okay, so you have a tape, right? Like, you have a buffer of memory. That was like step 1. And step 2 was, okay, now imagine you have this like thing that moves around and like reads and writes and shifts left and right. And so like the primitive pieces of the two worlds were just so different from each other that that's why they evolved up to one being immutable data and one being mutable data, and in those two different kind of branches of history. But the thing that I think is really fascinating is that as we've like learned stuff, as we've developed all kinds of new languages, new techniques, new principles, properties in each of the two branches of computer science history, we've just found out that there's just, and this is not a modern thing. There's actually a really cool paper that you can find that compares different points in computer science history where people in the field of computer science and the field of logic have stumbled upon the same idea and written papers about it with different names, and then somebody else later goes in and go, this logic principle and this computer science principle are the same thing. And the same thing is happening in the two branches of computer science history, where people are pulling ideas from one side and putting them in the other. So compiler theory is huge on the Turing side. Like, how do you make a programming language spit out the perfect set of instructions for a CPU so that thing runs super fast? Well, all that knowledge and history built up on that side of computer science history helped the functional programming side figure out how to build really awesome compilers for functional programming languages such that they could actually run in a reasonable amount of time and be useful for solving regular problems. And then on the functional side, we get stuff like immutable data structures and map and filter and reduce and all these really interesting concepts that make just as much sense in the JavaScript, C, Turing side, imperative mutable programming environments. We can reap very similar benefits from them on that side as well. So, really what this boils down to is that we have two branches of history, and we just have to be really careful not to be fully enclosed within one side of those. Otherwise, there's just this whole half of the world of tools available to us that we just would be completely ignorant of, and it would be invisible to us, and that would be sad.
Okay, so the connection is basically pedigree. You talked for 5 minutes, and I just boiled it down to one sentence. But yeah.
That's cool. That's what you do, and I do what I do.
That's right. So are there any other payoffs then besides the change detection and kind of the ease and speed of comparisons that you get from immutability?
That's definitely the big one. I mean, that change detection being super, super fast is definitely the big one. There's a handful of other ones that you get that are kind of side effects of that. One of them is, as the first thing that people bump into when they use Immutable.js, or the first experience with immutable data structures in any environment, is they realize that their habit up until that point for making something change in their app was to mutate the thing. And all of a sudden they realize that all of the ways that they've kind of structured apps before don't fit anymore, and they have to rethink things. And as soon as they do that, they find themselves pushing all of the mutation, all of the points where things can change to one place in their application, which can feel wrong from the sense of decoupling and making sure that each part of your application is well isolated and modular. And there's definitely ways to maintain modularity and still have this property of there's one place that things can change. But the really awesome thing that comes from that once you get there is that if there's some bug in your system where something is like changing in a way that you didn't expect, there's one place you go looking for that thing, right? And this like entire class of problem of race conditions, right? What's a race condition? A race condition is where two effects on the world can happen out of order from each other, right? And it's hard to figure out how that's happening. Well, that entire class of problems is dramatically reduced when you have a single point through which all edits need to flow, because you can just like say, okay, I'm just going to log every time an edit goes through here, and I'm just going to look at the order of the things that are coming out. You can't have two completely isolated parts of your application mutating things at the same time, unbeknownst to one another. That just, it doesn't happen anymore. It can't happen because of the nature of immutability. You can't just change that thing. You got to go figure out who owns it, and then say, well, here's the change I'd like to apply to the part of the app that owns that thing, and then let the app carry on from there. So I found that in the apps where we've kind of gone full force with this technique, that the kind of the bug tracking and fixing process ends up being much faster than in many of the apps that I've built before, just because the structure of the application makes it easier to figure those things out, and people step on each other's toes less often.
Do you feel like that's more because of the Flux Redux structure, because of immutable data? Like, or is it just to use immutable data, but not necessarily have in mind, say I had no idea what Flux and Redux was like, and I just decided to use immutable data. Would I see the same payoffs, or is it a combination of the two that actually is the payoff?
Well, I think you found the right keywords for the JavaScript audience of Flux and Redux. That is like the pattern that makes this possible. But the thing that you find out is that pattern, or at least a simplified version of that Flux or Redux pattern, is inevitable if you
sort of naturally emergent.
It is naturally emergent, exactly. There is just truly no other way to do it. You can't have multi-directional data flow because immutable data only goes one way. And so even if you had no idea what Flux or Redux were, but you did know what immutable data was, and you went off to build an application, you would end up rebuilding some version of Redux. I think Redux is a really nice version of that idea, but there's definitely 1,001 different ways that you could build something like Redux to work with immutable data. And actually, in some of the apps that we've built internally, we don't use Redux. We don't use the specific version of Flux that Facebook's talked about before. We've actually built something that's much simpler, that we know works super well with Immutable.js, and that worked particularly well with the quirks of the particular apps that we were building. It ends up just kind of getting built into the architecture of the app itself. But it is that pattern. It's exactly the same idea of one-way data flow. The kind of Redux reducer model is really handy for allowing, that's I think the key insight in letting you modularize your code, having different operations live in different files and being, they're not coupled with each other, but still having one place in the app where all those pieces then get knitted together in a nice bundle.
Now, we're heading down that road where we're getting a little more concrete, right? Where it's you start using this, you start seeing these effects, and it sort of converges on this kind of an implementation. So my question is, A, on a new app, should people just pull in Immutable and something like Redux, or should they evaluate to decide if they should put it in, and how do they do that? And the second question has more to do with existing apps, where I see that this might pay off. Cool.
I will tackle the first one first. So should you evaluate before you jump in? Absolutely. I happen to think that immutable data is a great solution to apps that have the problem of expensive render loops, where optimizing that render loop is something that you really want to do. So if you're building an app and you're starting, green slate, new file, open it up, try to figure out what to do next. If you envision in your mind that you're going to get to the point where that's going to be really important to you, then maybe you start off with Immutable. Especially since kind of the application structure is going to kind of dramatically shift towards a more Flux Reduxy style if you do that in the first place. If you don't foresee hitting those performance problems first, then maybe don't buy yourself that additional mental overhead of having to think that way first. However, I do think that it's worth considering the architectural concepts on their merit alone, even without pulling in the libraries. So even without pulling in Immutable.js or even without pulling in Redux, I think it's still worth considering immutability, single direction data flow, kind of more of a functional style to your application building from step one. Because if you do that, then if you later find out that, oh, wow, if this piece of my app had been immutable, then I could reap that change detection benefit here, and I would solve a massive performance problem. And it's a good thing that I made those architectural decisions early, because doing that should be pretty easy to do, and I could do that in a couple diffs. Whereas if you had built your app from day one with mutation and two-way data binding at its core, and then you later find out, oh man, if only I could memwise here, crap, I need to re-architect my entire app, then that would be really painful. And so that kind of leads into the second part of your question is, what about in my existing app? If I have an existing app, should I fold these ideas in? And if so, how do I even do that?
Well, especially on larger apps where there's more complexity and it's going to have more overhead to put it in. I mean, if you're early, it costs you less. If you're highly invested already in this application and it does a lot of stuff, it's right. Costly to fold it in.
Yeah.
All right, let's take a break and earn a little money for the show by talking about Hired.com. Hired is the world's most intelligent talent matching platform for full-time and contract opportunities in engineering, development, design, product management, data science, sales, and marketing. They put you in control, fill out an application, and then top employers apply to hire you. Throughout the process, your dedicated talent advocate will also have your back, providing unbiased career coaching to help you put your best foot forward with potential employers. And Hired offers access to more than 4,000 innovative employers, including big brand names like Facebook and smaller emerging startups. The size and type of company you want to connect with is totally up to you. And they help people find new opportunities in 17 major cities in North America, Europe, Asia, and Australia. So if you're open to relocation, you can let them know, and they'll work that in too. Finally, if you use our link, you can earn double the normal hiring bonus. The normal hiring bonus is $1,000, and they give you $2,000 instead. So go check them out at hired.com/JavaScriptJabber.
So I think especially for something that's big and complicated, the most important thing is to figure out what problem you're solving. So if your application is happy and its performance is reasonable, go work on something else, right? Like go add a feature, go fix a bug. If there's some part of your application that's just like critically performance intensive and it's just really slow to render or whatever, and there's a deep rooted performance problem, or there's some other architectural problem that you can kind of boil down to the fact that mutability at its core is the problem. Like you're seeing lots of race conditions is another variant of that, or another one that I haven't mentioned yet that's worth mentioning is you want to be able to do like an undo stack. So, I did A, then I did B, then I did C, and whoops, I didn't want to do C, go back to A. Whoops, I didn't want to do B, go back to A. doing that with immutable data is really easy because you just, the data didn't change, so you just keep a pointer to the version of the world before you did the change. If you didn't like what you ended up with, just go back to what you had before. It's extremely inexpensive to do that. And so if you've ever had to build an undo system for a piece of software before, I've had to do that before. It's pretty crazy. You have to think about everything's like inverse operation, and you have to worry about all the dependent effects that something could have and make sure you account for those as you're undoing something. It can get really complicated really fast. And the first time that I saw undo implemented with immutable data, my mind kind of melted out of my ears a little bit, just because it was so amazing. So I think if you're like faced with one of these kind of three problems that are the easiest or the most notably solved by immutability, undo stacks. So yeah, if you're building a big complicated app and you've identified one of these problems, the trick is, go in with a scalpel first, like try to figure out what's the smallest part of the app that you can change to start to fold these ideas in. Because rebuilding your app from the ground up with a new architecture is a harrowing task.
Oh, it's so much fun.
It's fun. It is fun.
All right, so I got a question for you.
Sure.
There are immutable operations on the built-in JavaScript array, right?
There are.
So instead of using Immutable.js, why would I not want to use the immutable, just treat an array immutable and use just its immutable operations?
Great question. So we talked a little bit about this sort of at the beginning of the talk here. The main one is the performance cost of that. So if you think about, so one of the immutable operations on an array, JavaScript array, is slice. If I want to take a chunk of that array, I can slice it. It doesn't do anything to the original array. I can then take my slice and I can change it, and I haven't affected the original array. So that is, in fact, an immutable operation. But slice costs you the creation of a new array, and then it costs you copying in the values in every item in that array. So one of the techniques that I've seen used before for implementing an immutable version of a JavaScript array is first call slice on the whole thing. So you get like a slice of the whole, and then that copies the whole thing, and then do whatever thing you wanted to do to it. So whatever, I wanted to update index 3, go do that. Or I wanted to reverse it, go do that. But of course, every time you call slice, you're copying the entire array, and then you're going through every item in that array, and you're copying it over from the original array. And so if you have an array of like 10 things, that's probably cheap. Like that's fine. That's going to be fast. But if you have an array of 1,000 things or 1,000,000 things, that's going to take a while. It's going to add up. And so that's the inherent difference between kind of the naive approach to immutability with existing data structures versus a new data structure to solve the problem.
Okay, sorry, go ahead.
That's it. Follow-up question?
Yeah, follow-up question on that. If it's an array of objects, does it do the same thing? Does it clone each object, or does it just simply create a second pointer to the same object?
It just creates a second pointer to the same object. And the same goes for Immutable.js collections, is that when you get a new version of a list back with your change apply, every item in that list is just a reference to the same thing. So
now, with Immutable.js, you also have an immutable object that corresponds with the immutable list, right?
Yep.
So if you're using immutable objects, then at the same time when you want to, all right, all that I want to do is change like the name of one of the users in the list, then I've created a new copy of that user object in addition to the whole new list that has the new copy of the new user object, right?
That's correct. Yep. You go all the way down in your data structure to the thing that you want to change. You change that thing, so you get a new version of it back. And then you've got a new version of that thing that you need to put into that containing list or whatever. And so you also have to make a copy of that containing list, which contains the new thing. And then now you have a new version of the list with the new version of your user object with its name changed within it.
Does that end up as being two operations using Immutable.js? Do you have to do those two things separately, or is it bound together?
There's one operation that you can do, because that's a pretty common one. There's an operation called set in, where you give it like a key path. So you say at index 3, and then at the key name, I would like this value. Fred. And then you get back an object whose name is Fred at index 3 in your original collection. So that all happens in kind of one line of code.
Okay. And that in and of itself also does that create a new list?
Yep.
Okay.
It creates a new version of everything that it touches down the way. So you could say, maybe you had like an array of user objects, and the user object had itself an array, and it had an array of, I don't know, pets. And so you wanted to like change in my third user's second pet's name change to something. It's like, okay, we'd have to make a new pet, and then a new list of pets, and then a new user since they have new pets, and then a new list of users.
But if I'm using just immutable operations on the built-in array, then how does that get complicated?
So now you're definitely, if you're just doing like built-in objects and arrays in JavaScript, that's definitely not one line of code. So first you got to like go find the thing that you want, copy it, make the edit, and then you have to like loop around and figure out where was that in the original one, copy that thing, edit, and then like you have to loop backwards until, so you could probably write a function that did that for you to make it one line of code. I mean, of course, that's all a library is making complicated stuff turn into one lines of code. But yeah, you would end up copying everything, right? Everything along that path would end up getting copied in the naive JavaScript approach.
So Immutable.js really gives you two big buy-offs. One would be the performance of doing these immutable operations. The built-in stuff just wasn't really built with this in mind. And then the second would be the nicety of the API.
Yep. You get a lot of really nice API tools that bring a lot of ideas from the functional programming world that has been dealing with immutable data structures for a very long time. So they've come up with lots of really awesome tools and techniques for working with them. But they're kind of rephrased in terms of method names that JavaScript engineers are more familiar with.
Gotcha. Cool. Well, I think that's all my questions.
Awesome. Hopefully I didn't ramble on for way too long.
No, I just sat here and learned the whole time. It was really good. Thanks.
Yeah. What would you say the learning curve is like picking up Immutable.js? Say that you were reasonable at JavaScript, and you understood how to do mutable operations well enough, and you decided, hey, I want to do this whole immutable thing and give it a try. What's the learning curve like?
I think there's kind of like two jumps on the learning curve. For the most part, I've found it's pretty easy because most people don't have to dig in under the hood and figure out what these things are actually doing. They're just using them. So the first jump is just like grappling with the idea of immutability in the first place, like understanding like, oh, right, like you just have to continue to check that initial instinct to mutate data. Every time you encounter one of these, you're like, right, I can't do that. Okay, how do I restructure things again to make sure that this is happening immutably? And so after a little bit, that becomes kind of second nature. You get over that pretty easily. And the second one is that more like thinking architecturally, like making sure that your entire app has single directional data flow. It's much easier to understand how like, oh, right, I have a list. I want to push onto that returns a new list. I got to make sure that I use that instead of my original list. Like that's pretty easy for people to wrap their heads around. Getting to the point where you're more comfortable with not just Flux and Redux, but like understanding why Flux and Redux work the way they do, and not just using those libraries, but using the architectural techniques that they provide everywhere in your application. That's really the secret to getting the most out of immutable data structures. And I think that's probably the second learning curve. The third learning curve is not for the faint of heart, which is actually diving into the code base and contributing to it, making performance improvements, stuff like that. Very few people end up there though, and that's fine. That's how it's supposed to be.
Right. What about like official documentation? How good is the documentation that exists for Immutable.js, and are there other learning materials that are out there that people should know about?
Well, there's a bunch of learning materials that are out there that you can go Googling for. Most of them are in the form of write-ups on blogs that I think are really helpful. The Immutable.js docs themselves, they're a reference doc. So they'll go through all the methods, what they do, how to use them, the arguments that you can provide, stuff like that. The official docs have some instances of example uses, but not as much as I'd like. So it's one area that I'm hoping to see our official docs improve. is more just like, hey, I want to do ABC. How do I do that? And just have like a lot of usage examples. So that's where I think blogs examples have filled in the blanks, but we'll get there.
Awesome. Finally, I do have one more question for you.
Sure.
My wife told me that I should wear more bow ties. Is there something you can help me out with?
Yeah, bow ties are cool. So for anyone who's seen me do a conference talk before, have probably noticed that I usually wear a bow tie when I do talks, which started as almost like a joke. I actually love bow ties, and I wear bow ties at every formal event. And one of my coworkers asked me, before I did one of my first conference talks, I want to say it was like 2003 or 13 or 2014, in a while, he asked me if I would wear a bow tie at my talk, since he always saw me wear bow ties at like events and parties. And I was like, that would be funny. And he's like, yeah, it would be funny. And I was like, actually, that would be a cool idea. I'll just do it. And then I got so many reactions out of it. People were like, I love your bow tie. This is great. Nobody ever like dresses. Everyone just like wears hoodies at these conferences. It's cool to see someone dress up a little bit. So I was like, that was kind of cool. So now every time I do a talk, I wear one of my bow ties. And of course, I really like bow ties. I collect a bunch of bow ties to wear at more events than just doing conference talks. One of my favorite shops is called Knotty Co. Of course, it's like KN, not like knot, tie and knot, Knotty Co. They have lots and lots of really cool bow ties. It's one of my favorite shops. And I have some others, but I have to keep them secret.
You got to keep them secret. Why?
Because all your listeners will buy them out.
Yeah. No, it's good. It's Chuck. It's like when you know where to catch the good fish. You don't tell anyone. I get it. Makes sense.
But I gave you my best source. Knotty Co is definitely the best one.
All right.
Well, should we go ahead and do some picks?
Sure.
I'm gonna make Joe start.
You want me to start?
Yes.
Can I go second?
Sure.
You go first, Chuck.
Do you have some picks? Oh, you want me to go first?
I got a pick. My pick is called. It's a book. It's called The Contractor. It's actually called Contractor. It's book 1 in the Contractor's book series, and it was a cool read. It's about Earth being invaded, and there's just mages around to save people, and it's kind of a weird magic story, but I thought it was really cool. I really liked it. I couldn't stop reading it once I started it. So, The Contractor. It's a good book. That's my pick.
All right. I'll go ahead and jump in with some picks. I have a new system I'm trying out, and if you're running a business and you're looking for a CRM, so far it looks pretty promising. It's called 17 Hats. It's 17hats.com. And I'll put a link in the show notes with a referral code. But basically, it allows you to keep track of relationships with people and set workflows and things like that. So for me, it's particularly helpful because I'm currently using a Trello board to keep track of progress and who I need to keep in touch with for sponsorships and speaking at the remote conferences and stuff like that. And something like this where I just have a workflow. So it's, hey, I reached out to this person about speaking, and I just have them in the system, and then the workflow, reminds me, okay, it's time to follow up again, or it's time to send an invoice, or it's time to, talk to them, or it's time to get their information so they can speak, or what have you. Anyway, that's kind of a system that I've been looking for, so I'm definitely checking that out. And then the other system that I've been using, and I've been using this with some of my subcontractors for some of the podcast stuff, is Asana. And there are a couple of things I really like about Asana. One is that I've actually created template projects for some of the checklists I have. And then what I do is I just copy the project, and I have a project that's all set up for the next remote conference, and I can just work down the list. And that's really, really handy. The other bit of info on that is that it integrates with Zapier and Slack. And so it does a whole bunch of stuff just that way, kind of automatically. It also integrates with things like calendars and stuff like that, but I haven't done much with that yet. However, since it integrates with Zapier, I can tie it into pretty much anything else. So I'm really, really digging it, and it's working really well. Joe, do you have some picks for us?
You bet. So I would like to pick a video game I've been playing recently. I picked up Call of Duty Infinite Warfare on the Steam Black Friday week sale. And it's been awesome. It's been an amazing game. But what's amazing about it is it's single player. I understand it's multiplayer isn't that great. I haven't even bothered trying to play the multiplayer. But for some reason, I've played a couple of these Call of Duty games. Their single player campaigns are just so fantastic. Like, they should be movies. They're so well, the story is so interesting and so well written. So I've really enjoyed that. I highly recommend it, Call of Duty Infinite Warfare. And I also want to pick Lego Star Wars sets, not like video game. I'm talking about the actual, like, physical, you go to the store and you buy the set and put it together. My son's 12. He loves Star Wars. I love Star Wars. So recently I bought quite a few of these Lego Star Wars sets. I even bought one for my daughter because she was way into Kylo Ren. And we put them together, and they've been really fun to do with my kids. And just, I've really enjoyed the time and enjoyed having them. So that's going to be my second and final pick is Lego Star Wars.
Alrighty. Lee, what are your picks?
Well, I already picked Knotty Co for your bow tie needs. Let's see. Another one is Advent of Code. I don't know if you've seen this before. It's like a puzzle site, but it's like an Advent board. So it works its way up to Christmas Day. And every day there's a couple puzzles that you solve. And it's actually really hilarious. Like, each puzzle is, they're little, like, tiny computer science puzzles that you should be able to solve in like a half hour or so. But they all have this storyline where, like, Santa's core technology has been stolen by the Easter Bunny, and you have to, you're sent out on a mission to go steal it back, and the Easter Bunny keeps, like, throwing stuff in your way that you have to solve. So it's very cutely written, and it's very funny. And the puzzles are fast enough to solve that it doesn't take very long, but long enough that it holds your interest for a while. But I don't know, I've been going through a couple of them, and they're a lot of fun. So adventofcode.com, worth doing.
All right. If people want to follow up with you, see what you're working on, follow you on Twitter, read your blog, whatever, what do they do?
Definitely follow me on Twitter. I tweet reasonably often, and I usually tweet about the stuff that I'm working on. So follow me at Twitter. I'm at LeeB, L-E-E-B, on Twitter.
All right. Well, we'll go ahead and wrap this show up. Thank you for coming, Lee.
Yeah, thanks, Lee.
Yeah, my pleasure.
All right. We'll catch everyone next week.
Peace.